Wow, go on my GCSE science students, welcome back to another video. Now in today's video we're going to be looking at chapter 5 for the chemistry paper 1, which is known as chemical changes. Okay, so in this chapter we're going to be looking at the reactivity series 5.1. We're going to be looking at displacement reactions. How do we extract metals? We're going to be looking at salts from metals, salts from bases, and salts from alkalis and carbonates. Okay, so on we go. So now let's look at the reactivity series. Now, what exactly is the reactivity series? Now, a reactivity series is just a group of metals, all right, in a particular order that we can use to make predictions about certain reaction. And this is the reactivity series that you can see here, starting from potassium at the very top, which is the most reactive, all the way down to gold and even platinum at the very bottom. Okay, now these are not all the metals, but these are just the common ones, going from the most reactive to the least reactive. And as you can see here, we're using a mnemonic that we can use to remember this. All right, so please stop calling me a careless zebra. Instead, try learning how copper saves gold, and don't forget platinum at the bottom, even though it's not shown there. Okay, so please, potassium, stop sodium, all the way down to gold. All right, now you can come up with your own mnemonic for trying to remember this, and sometimes it is given on the exam paper, but not all the times. Okay, so what do we use this to do? We use it for predictions that can be made about simple reactions, all right, with metals, oxygen, water, and acids. And predictions can also be used from the reactivity series about more complex reactions. Okay, now if you notice in the reactivity series, you're seeing carbon here, which is in red, and you're seeing hydrogen there, which is in red. Now the first question that I'm asking here is, why are they in red? Now they're in red because they are non-metals. Okay, so that's the reason that they're in red. They are non-metals, and the reason that they're there is so that they can be used for comparison. Okay, so they're there because they can use for comparison. So that's the reason these two non-metals are there. All right, now in terms of the reactivity series, you'll notice that the most reactive elements at the top, the most reactive metals here at the top, those are in group 1. All right, and they're most reactive because they only have to lose 1 electron. And then if you go down here, it's going to be group 2. All right, because they only have to lose 2 electrons. Then aluminum is in group 3, and then you notice that these down here, these are now your transition metals. Okay, so the most reactive metals are in group 1 because they only have to give up 1 electron in their reaction, and then calcium, magnesium, they would have to give up 2 electrons in their reaction. Okay, all right, so the other thing that you need to know for this chapter is these reactions. All right, so when you react a metal with oxygen, it will form metal oxide. Okay, so for example, if you're reacting iron with oxygen gas, you are going to form iron oxide. Or if you're going to react sodium with oxygen, it's going to form sodium oxide. Or calcium with oxygen, calcium oxide. You get the idea. Okay, now if you're reacting the metal with water, you will form the metal hydroxide and this gas, hydrogen gas. Okay, and hydrogen gas. All right, so for example, if you're reacting iron with water, you are going to form iron hydroxide. Very simple. And you're also going to be forming hydrogen gas. Okay, good. And then if you're reacting a metal and acid, you will always form salt and hydrogen gas. Okay, MASH. You can use MASH to remember that. Okay, good. So for example, if you're reacting iron with, let's say, hydrochloric acid, you are going to form iron chloride, which is the salt, plus hydrogen gas. Comment below to let me know how do you test for hydrogen gas, okay? And I'll check the answers and see if you got that correct. All right. So here are the examples that we spoke about. If you're reacting iron with water, it would form iron hydroxide and hydrogen gas. And if you're reacting iron with hydrochloric acid, it would form iron chloride and hydrogen. And I've done the equations for you guys, balance equations. Now, as you can see below, there are these bits of the equation, which you should know that those are called state symbols. So here are the different state symbols that you need to know. So if it's a solid like iron, for example, that's a solid at room temperature, you're going to put a lowercase s. L for liquid, lowercase, and G for gas. Okay, and if a substance is soluble, it's going to be aqueous, or if it's in a solution, it's going to be aqueous. Okay, so let's do a quick check to see if we understand. What would this form? This would form sodium oxide and nothing else, just sodium oxide. Okay, so let's write an equation for that. Sodium is a solid, okay, Na. Oxygen doesn't exist as just O, it's O2, it's diatomic, okay, and that's a gas, and it will form sodium oxide. So Na2O. For those who are not sure how we got there, sodium is in group 1, so it's +1. Oxygen, it is in group 6, therefore it is -2. Stop, we drop, and we swap. Okay, so this is 2, this is 1, therefore the formula is Na2O, and that's going to be a solid. Of course, this is not balanced because I have 2 on the right side. Please check out my video for balancing equation. So I'm going to put a 2 there. All right, good. So hopefully you realize what to do there. All right, let's clear this. And then let's try the next one. So sodium plus water, that's going to form, remember we said it's going to form the corresponding hydroxide. And it's also going to form hydrogen gas. Okay, so sodium, Na, plus water, H2O. All right, sodium is a solid, water is a liquid, and it's going to form sodium hydroxide, NaOH, and hydrogen gas, H2. So that is going to be aqueous because it's soluble in water, and this is hydrogen is a gas. Of course, this is not balanced because I have 1 sodium there, 1 there, 2 hydrogen there, but I have 3 hydrogen on the right hand side. So if I put a 2 there, that hydrogen now becomes 4. We need to put a 2 there. To put a 2 there, let's do a double check. 2, 2, 4, 2 hydrogen there, and another 2 makes it 4. 2 oxygen, 2 oxygen. Equation is balanced, okay, with state symbols. All right, good. Let's try another one. Sodium and sulfuric acid is going to form the salt, which is called sodium sulfate. And it will also form hydrogen gas because it is a metal plus acid. So sodium, Na, plus sulfuric acid, H2SO4. You need to know the formulas for your acid. It will form Na2SO4 because sulfate is a 2- charge. If you're not sure how to do the formula writing, please check out my video for formula writing, okay? And hydrogen, H2, okay? So again, this is not balanced, so we're going to put a 2 there. 1 sulfate. Okay, everything is balanced. Don't forget your state symbols. That's going to be aqueous. This is also going to be aqueous because it's soluble. Hydrogen is a gas. Okay, good. Let's clear that one. Let's try another acid. So this time it's going to form sodium chloride because the acid is hydrochloric acid. So it's going to form sodium chloride plus hydrogen gas. Okay, so it's going to be Na plus HCl, and that will form NaCl, aqueous, okay, plus hydrogen gas H2. Now this is not balanced, so we need to put a 2 there. That makes it 2Cl. By the way, this is, let me just get my eraser and make that better so it doesn't confuse you. Oh. Alright, so let's go again. So this is now going to form sodium chloride. Okay, and it is also going to form hydrogen gas. Hydrogen gas. So it's going to be Na solid plus HCl aqueous. Okay, that's going to form NaCl aqueous and H2 gas. Now this is not balanced because I have 2 hydrogen there, so I need to put a big 2 there. That's going to give it 2Cl, so I'm going to put 2 there. Then you need 2 sodium there. Equation is balanced. Alright, you need to know the formula for your acids. So what I've done here, we're now looking at all 3 acids, and then we have nitric acid. So that's going to be sodium nitrate plus hydrogen gas. Okay, so it's going to be Na solid plus HNO3. All right, aqueous. All acids are aqueous. Okay, unless they state that it is not diluted, it's concentrated, then it would be a liquid. So that's going to be NaNO3 and H2. All right, and this equation, by the looks of it, it is all balanced. 2 hydrogen. No, it is not balanced. So we have 2 hydrogen there. We have 1 here. To put 2 there, 2 there, and 2 there. So it wasn't balanced. All right. So these are the general reactions that you need to know for metals. So metal plus oxygen, metal plus water, metals plus acid. All right. Make sure you know all of those. All right. So moving on now to displacement reaction. Now, what exactly is a displacement reaction? Now, a displacement reaction is a reaction in which one substance takes the place of another, or it displaces it. So as you can see here, I have a piece of zinc. That piece of zinc is placed inside some blue copper sulfate. If you notice now, the copper sulfate solution is becoming less and less blue, because what is happening is that the zinc is taking place of the copper. Okay, so a displacement reaction is where the more reactive metal takes the place of the less reactive metal from its salt solution. Okay, so for example, we know that copper is less reactive than zinc, and we know that from the reactivity series. I'm going to put that up back in a bit. Therefore, it will displace copper from its solution. All right, and here is a reaction just to show that zinc has now taken the place of copper. So notice now where copper is, right? It's been taken by zinc and knocks out copper, which then is by itself there. Okay, good. So copper does not displace zinc from zinc sulfate solution because copper is less reactive. Okay, so here is another way we could look at it. So you can see here a cartoon displacement reaction. All right, so you have Mr. Copper and Miss Oxide being married together. They are now called copper oxide. And here come Mr. Magnesium. Magnesium, more muscly, okay, is going to displace copper from oxide, and therefore what you're going to end up with now, Mr. Magnesium and Miss Oxide to form magnesium oxide, and copper is all alone by himself. Okay, so that's a simple way of looking at it. Magnesium, more reactive than copper, therefore it can take the place of the copper. Okay, it's displaced copper. All right, so as I said here is the reactivity series that we spoke about. Please stop calling me a careless zebra. Instead, try learning how copper save gold. Remember, I said that there are other elements there, but those are just the main one that you need to know. So let's look at this one. All right, can sodium take the place of zinc? So let's look for sodium. Let's look for zinc. Yes, sodium can displace zinc. Okay, sodium can displace zinc. Therefore, what are we going to form? We're going to form sodium sulfate. Okay, and zinc is going to be all alone by itself. Again, if you're not sure how I got Na2SO4, go to my video for formula writing. Okay, and this is not balanced, so we need to put a 2 there. Okay, and everything else is fine. Okay, so therefore sodium can displace zinc. Now let's look at the next one. Where is my eraser? Let's grab my eraser here. All right, good. So zinc and zinc. Okay, that's not going to be a reaction. All right, zinc won't take the place of zinc, so that's going to be no reaction. Let's look at copper and zinc. Let's look for copper and zinc. Can copper take the place of zinc? No. How do we know that? Because copper is less reactive. It's lower down in the reactivity series, and therefore that's going to be no reaction. Copper cannot displace zinc. Okay, so hopefully you have a better understanding of displacement reaction here. All right, now displacement reactions are also what we call redox reaction. Now what exactly is a redox reaction? A redox reaction is one in which both reduction and oxidation takes place at the same time. Now by reduction and oxidation, reduction is the gain of electron and oxidation is the loss of electrons. All right, you can use this mnemonic if you are not sure. Oil rig. So what does oil rig mean? Oops, oil rig means that oxidation is the loss of electrons. Okay, good. And reduction is gain of electrons. Okay, so that's what you just need to remember there. So let's look at an example. You need to be able to, and this is for higher students only. So if you're watching this video in your foundation, you don't necessarily have to watch this part, all right? Because writing ionic equations is for higher students only. So let's look at this. Now we're going to write an ionic equation, and when writing ionic equation, the first step is that we split up all the ions and add the charges. And I'll go even further, and I'm going to add in the state symbols, okay? And I would say only split the ones which are aqueous. Do not split solid. Do not split liquids, okay? Or gases. So do we split the zinc? No, we do not. Okay? Because and again, it's not made up of ion. Do we split the copper sulfate? Yes, we do. It's going to give me Cu2 plus aqueous. And it's also going to give me SO4 2 minus aqueous. Okay, good. And are we going to split the zinc sulfate? We definitely will split the zinc sulfate. It's going to give me Zn2 plus aqueous and SO4 2 minus aqueous. And copper, we do not split that as it is a solid. Okay, so that's step one. We split up all the ions and add the charges. Step two, we find the ions which doesn't change and cross them out. So if you look here, Cu2 plus, all right, they're different because this is copper solid. But look at this, SO4 2 minus and SO4 2 minus. All right, let's use a different color there. They're common. They're called spectator ions. Okay, which then takes me to step three. Rewrite the equation out with the charges. So we're going to rewrite what is left behind here. So we have your zinc solid, then you have your copper 2 plus aqueous, and that will then form Zn2 plus aqueous and copper solid. Okay, and this is now what we call an ionic equation. Okay, that's now called an ionic equation. All right, so those are the three main steps for writing an ionic equation. We will do one more, okay? So I just add the state symbols in so that it makes things easier. Okay, remember only, oh, that is really bad writing there, oh, because I'm trying to write quickly. AQ, and then that one there is a solid. So step one, we split up all the ions. All right, sodium is not an ion, therefore we don't split. Zinc sulfate, that has ions, so we are going to split. SO4 2 minus. You need to know your ions. Okay, that's going to be Na plus aqueous plus SO4 2 minus aqueous, and then that's going to form zinc, not an ion, therefore we don't split. Then we go to our next step where we're now going to cancel out our spectator ions, SO4, SO4, and then we rewrite this. What we have there, NaS plus Zn2 plus aqueous, we will form Na plus aqueous plus Zn solid. All right, and this is now your answer for the ionic equation. Okay, good. All right, so on to the next chapter. Oh, before I move on to the next chapter, it's very important that you have a look here. Sodium went from being no charge to having a +1 charge, which means it's lost electron. Yeah, so if you look at it, it was single and now it is married to sulfate. So what has happened there? It has lost electron, therefore it has been oxidized. Okay. Then if you look at the zinc here, it was married and then it now becomes single. Therefore, we could say that it is now become reduced. Okay, it's now been reduced, and therefore this reaction is a redox reaction. Okay, good. We can look at this later on. All right, so now we're going to look at metals from ores. Okay, so firstly, where do we get metals from? Metals, we get that from the Earth's surface, the crust. Okay, and so we get most of the metals that we get in today's world. We get them from the crust, so things like aluminum, gold, silver, platinum, all of these metals, copper, we get them from the Earth's crust, okay? Now, can we use them straight out of the ground? Not in all cases, okay? So sometimes they need to be purified. Well, not sometimes, all the time. They do need to be purified. They do need to be separated because sometimes they are combined with other elements. Okay, so metals, some metals are found in their native state, so uncombined. So things like your silver, your gold, your platinum, those are found as native elements. They're uncombined. So you don't have gold oxide, silver oxide, platinum oxide, they're uncombined. All right, so these are least reactive. They're found at the bottom, so they do not react. Okay. And what exactly do we use these metals for? We use them for things like jewelry. We use them to make conductors, pots, pans, aeroplanes, anything like those. Okay, so how does the reactivity make them suitable for their uses? So these at the bottom, because they're unreactive, they can be used for things like jewelry. Okay, so you're not going to be wearing your jewelry and think, oh, it's going to rust, or well, not rust, rather, sorry, corrode or react with water or anything like that. All right, so here are all the answers to the questions that we were asking before. All right, so they would not have been reacted with any metals. They're used for jewelry, metals, all of those things, and they will not react. All right, so they're found as native. The ones which we call native are at the bottom. They're unreactive, uncombined. Now, some metals, they can be found as ores, the more reactive ones, these ones at the top. These are found as ores, like aluminum oxide, sodium oxide, things like those, okay? They're found as ores. From copper going upwards, they're found as ores. All right. Now, if a rock contains a high enough percentage of metal and that you can extract it and make some sort of profit, we call that an ore. And that's a definition that you definitely need to know. All right. So an ore is a rock which contains enough metal to extract it and make some sort of profit. All right. Now, if you look at the top here, in order to extract these metals, when we're extracting them from their ores, we must use electrolysis, okay? And I'm going to be putting up my video. You can have a look through my channel for my video on electrolysis, okay? Those below carbon, we can displace those elements, all right, with carbon. So you can carry out a displacement reaction by heating it with carbon, okay? Good. And those below here, those are found in their native states. Okay, those are found in their native states. Now, the type of bonding that will be found for those minerals here at the top is going to be ionic because it's metals with non-metals. And yeah, so the reason that we use carbon for those in the middle is because carbon is fairly easy to produce and it is in lots of abundance. Carbon is cold, okay? All right. And if our ore contains a metal less reactive than carbon, then we could carry out a reduction reaction, as we said here. So at the top, electrolysis. Below carbon, we can displace it or reduce it with carbon. And then in that process, the carbon is then oxidized, okay? Also, we can carry out a reduction reaction with hydrogen. So your less reactive metal than hydrogen, I'll show you here, you can reduce them with hydrogen. So if you had something like copper oxide, you could react that with hydrogen in a displacement reaction, okay? For example, let's have a look at tungsten, which is less reactive than hydrogen. What will happen is that your hydrogen can displace your tungsten to then form tungsten by itself, now being displaced, and water is one other product, okay? Good, so that's another reaction that can be carried out, okay? All right, so one other thing that we needed to talk about here as well. So if we're looking at something like iron oxide, FeO, we could react that iron oxide with carbon. Okay, now a displacement reaction will take place. Why? If you look at this, carbon is more reactive than iron. Okay, so carbon is more reactive than iron. Therefore, what is going to be formed? We're going to form carbon dioxide. Oops. We're going to form carbon dioxide. And iron is going to be by itself. So iron has now been displaced, okay? So it's not balanced, so we need to put 2 there, okay, to make it 2 oxygen, and we need to put a 2 there, okay? So now that displacement reaction has occurred. So that's how we do that reaction in terms of displacement with carbon or heating it with carbon. So to summarize, those at the top, we use electrolysis. Those below carbon, we can displace it with carbon because carbon is in huge abundance. And those at the bottom, they're found in their native states. Okay, good. Now, let's look at how do we form salts from metals. Now, when you react metal and an acid, we did discuss this earlier, but just to remind you, metal plus acid will form salt and hydrogen gas, and I can use the mnemonic MASH to help you to remember that, okay? So MASH, okay? So metal plus acid will always form salt and hydrogen gas. So for example, calcium and hydrochloric acid will form calcium chloride and hydrogen gas, and here's your equation there. It isn't balanced, So we put a 2 there, okay? Now, just to remind you that there are 3 acids that you need to know. Hydrochloric acid, HCl, sulfuric acid, H2SO4, and nitric acid, HNO3. So, if we were to complete these worded equation, and this provides the last name of the salt being formed. So calcium plus nitric acid, it will form calcium nitrate and hydrogen gas. Always. I'm just going to put the formula there, okay? Well, it said worded equation and hydrogen gas. All right, lithium plus sulfuric acid, what will it form? Lithium sulfate and hydrogen gas. Hydrogen gas. Okay, so magnesium and hydrochloric acid is going to form magnesium chloride. Magnesium chloride. And also hydrogen gas. Okay, good. All right, so just remind yourself that metal plus acid will form salt and hydrogen gas. Now a base, we're now going to look at what exactly is a base. Now base is any substance which can neutralize an acid, and when we talk about a base, we talk about metal oxides or metal carbonate. So for example, you could have copper oxide is a base, sodium oxide is a base, sodium carbonate is a base because they are metal oxides or metal carbonates. All right, now some bases are soluble, and those bases which are soluble, we call them alkalis. Okay, now we're going to be looking at salts from bases. So remember, a base is any substance which can neutralize an acid. Now what I used to remember is that when you react a base and an acid, you will form salt and water. So if you look here, another mnemonic sticks out. Okay, basho. Base plus acid forms salt and water, okay? So a base is any substance that reacts with an acid to form salt and water only, and this is called a neutralization reaction, all right? So as we said, remember, metal oxides are bases. For example, copper oxide, calcium oxide, sodium oxide, those are bases, all right? Now let's see if you fully understand what's going to happen here. Calcium oxide, which is a base, reacts with nitric acid. Remember, it's going to form calcium nitrate, and my other product will be water. Okay, so lithium sulfate and water, and magnesium oxide and hydrochloric acid is going to form magnesium chloride and water. Okay, again, need to know your acids. You can try writing the balance equation for these. Okay, so what exactly is a salt? A salt is just an ionic compound formed with anions and cations, and soluble means that it's able to dissolve in water. So a soluble salt is, could you put your definition down in the chat? Just put those two together. So a soluble salt is an ionic compound which is able to dissolve in water. Now, a soluble salt can be made, and this is one of your required practical that you need to know, by reacting an acid with an insoluble metal oxide. And here are the general steps for making a soluble salt. You mix the acid and the insoluble oxide, you warm them to react, you then filter, and then you evaporate and crystallize. Okay? Now, why do you think step 3 is to filter? Remember that we're dealing with an insoluble metal oxide. So for the bit that was unreacted, that's why we're going to filter. All right. And why do you think we add excess, or we're mixing this excess? Because when we're mixing this, we need to ensure that we're using an excess amount of the metal oxide. Now that is done so that it can react with all the acid there. All right, so just remember MWFE. Okay, come up with some mnemonic for remembering that. Those are the 4 general steps for making a soluble salt. So in your required practical, you were making copper sulfate, but in the exam they can ask you about any soluble salt. The steps are similar. So these are all the equipment that you need. You can see your acid, the sulfuric acid, and your copper oxide, because remember we're trying to make copper sulfate. Okay, so if we're trying to make copper sulfate, the two reactants that would be needed must be sulfuric acid to make the sulfate and copper oxide. You could use copper carbonate as well as the base, okay? And of course, one of your other product is going to be water, but remember that it is soluble, so that's why we have the evaporating dish. So let's look at all the steps here. Now in step one, you're now adding your sulfuric acid to the beaker, okay? And then you're going to warm in a water bath. The reason that you're warming is so that the reaction can happen quickly. Then you're going to add your copper oxide in excess. Now, how do you know when this is in excess? Is that you're going to see solids of copper oxide being at the bottom that has not yet dissolved. Now, your next step is that you're going to be filtering. So at the bit here is going to, the residue is going to be your unreacted copper sulfate, so copper oxide rather, your unreacted copper oxide, okay? Then after you filter, you're going to pour in an evaporating dish, because remember that it is a soluble salt, and then you evaporate, and then you leave your crystals to dry. All right, you leave it to crystallize, and then you can dry with a paper towel or put it in an oven to dry. Okay, so remember your key steps are: step one, you mix the reactants in excess, you warm so that it reacts faster, you filter to remove the excess base, and you heat to evaporate or crystallize. Okay, good. Now, our next reaction is between carbonates and acids. Now, when you react a carbonate and an acid, it forms salt, water, and carbon dioxide. All right, you can use Kashoka to remember that. So, carbonate plus an acid forms salt, water, and carbon dioxide. Comment below, how do you test for this gas? So, let me know, how do we test for carbon dioxide gas if you know. All right, so let's look at these reactions. Remember, carbonate plus acid, it will form salt, water, and carbon dioxide. So if I have calcium carbonate here, it's going to form calcium nitrate. It will always form water and carbon dioxide. Okay, so if I have lithium carbonate here with sulfuric acid, it's going to form lithium sulfate plus water plus carbon dioxide. And if I have magnesium carbonate and hydrochloric acid, it will form magnesium nitrate, magnesium chloride rather, apologies, water, and carbon dioxide. Okay, good. Now, we're now going to be looking at pH as well. All right, so all acids, if you look, you need to know the formula for all these acids. All acids, they contain hydrogen. So an acid is any substance which releases hydrogen. Even have a look at vinegar here. Ethanoic acid, it has a hydrogen which can be released. So all acids contain your hydrogen ion. So if you have a look at pH, okay, so pH really just means the amount of hydrogen, the power of hydrogen. Now have a look here at the pH value as you move from 1, 2, 3, 4, and so forth. What do you notice is happening to the amount of hydrogen ion concentration? And by the way, this is higher content, okay? So as you move from a pH of 1 to 2, you notice that the amount of hydrogen ion present becomes 10 times less, okay? So this is 0.1. This is now going to be 0.01, and this is 0.001, 0.0001. So as the pH increases, the amount of hydrogen ion concentration decreases by 10-fold. So if I had a pH of 6, it's going to be 1 times 10 to the minus 6 in terms of the amount of hydrogen present. All right. So the lower the pH value, the more hydrogen that is present. All right. Now, all acids, as we said, higher content, all right, will release or ionize to form hydrogen ions when dissolved in water. Okay. Why can we safely put dilute solution in our chips? And it's not a bad, and it would be a bad idea to put sulfuric acid, because ethanoic acid is a weak acid. Okay. So you can see your strong acids here, your weak acid. So weak acid versus strong acid. What do we mean by that? The difference is how readily they ionize or readily they break up in a solution. All right. So as you can see here, sulfuric acid breaks up to give all of its hydrogen ions there. Okay. But in terms of a weak acid, if you notice here, look at the amount of hydrogen. We have 4. However, it's only produced 1. Therefore, that's why it's weak. It's only partially ionized. Okay, so the difference between a strong acid and a weak acid is that a strong acid completely ionizes, but a weak acid partially ionizes in the presence of water. And as you can see here, this means that the reaction is reversible. Okay, good. So here is the partial ionization, all right, which we were talking about before. It only partially ionizes. So you can see 4 on that side, but it's only produce 1. All right. We will look later at the position of the equilibrium in a later lesson. Okay, but this is exactly what you need to know in terms of partial ionization. Now, alkali. Alkali is any substance which releases the hydroxide ion. All right, so any substance which, when ionized in water, releases the hydroxide ions. And the formula, you need to know the formulas for your alkalis. All right, so you can see here sodium hydroxide is NaOH, potassium hydroxide is KOH. All right, now you need to be, how does this link to the pH scale? You can see the lower the number, the more hydrogen ions it has, but the higher the number, the more hydroxide ion it has. Okay, so you can see the different examples, and right here in the middle it has equal number of hydrogen and hydroxide ion. Okay, so remember, the lower the number, the more hydrogen ions, the higher the number, the more hydroxide ions that it has. All right, now how do we measure pH? There are 2 different methods we can measure the pH. We can use the universal indicator, or we can use the pH probe. All right, other ways you can measure pH, but you can use other indicators such as litmus and methyl orange, but universal indicator will give you the exact pH, and the pH probe or the pH sensor will give you the exact pH. Okay, what would happen to the pH of sodium hydroxide? So this is in my container of sodium hydroxide, and we're adding hydrochloric acid. So in other words, we're adding an acid to an alkali. What would happen? Now your pH is going to increase. So if we carry out this practical and we look at this, the pH would start here. So on this side it's going to be pH, and on this side of my graph it's going to be volume of HCl added. Okay, so my pH meter is inside my alkali, so it's going to start at a high pH. All right, then it's going to make a sudden drop, and then it's going to level off somewhere there. At this point, that point there is going to be known as my neutralization point. Okay, this will roughly happen at a pH of 7. Okay, good. Now that summarizes all of this chapter. Please share, like, and subscribe. Remember, all the best in your GCSEs, and I am out.